In this lesson, we're going to introduce something called higher order derivatives in order to extend our study of differential calculus. We'll begin by seeing how to find higher order derivatives. We'll then see how to incorporate them into our notation for derivatives. And finally, we'll look at a physical interpretation of one particular kind of higher order derivative called the second derivative. Let's start by seeing how to find higher order derivatives. In terms of where we are in our course, we're taking a short break from our study of derivative rules. This has been our focus lately. We've been establishing rules for finding derivatives of different kinds of functions without relying directly on the fairly complicated limit definition of a derivative. And at this point, with the rules we now have, we can take the derivative of any polynomial function as well as any rational function, and that includes constant and linear functions, by the way. We also know how to take the derivatives of some radical functions and the trigonometric functions. We're now going to take a short break from introducing derivative rules. We're going to look at a slightly different aspect of differentiation. And then after that, we'll turn back to a continued study of derivative rules in order to be able to take derivatives of functions we can't yet handle using our current rules. So to get at the idea of higher order derivatives, let's think about repeated differentiation. The key here to note is that, as we observed earlier, when we take a derivative of a function or differentiate it, the result is another function with the same independent variable. So to take an example, if we start with the x cubed function, call that f of x, and we want the derivative f prime of x, it will be 3x squared. And 3x squared is a function of x all by itself. So one of the things we can do with 3x squared now is to take its derivative with respect to x. And then we can repeat this. We can keep taking the derivative or applying the differentiation operation again and again and again. So if we take the derivative again, going from x cubed to 3x squared and then applying the dx operation once more, we get 6x. Take the derivative again and you get 6. Take the derivative of that and you get 0. Keep in mind here that you can think of 6 and 0 as constant functions. So you can still think of them as functions of x. They're just kind of boring functions that give you the same output for any value of x. So what we just introduced was the idea of a higher order derivative of a function. These are what we get when we start with a function f of x and then differentiate it more than once. The results are the higher order derivatives of our function f. Most of the time when we're talking about these things, the really important one is the function we get when we differentiate twice. And we call that the second derivative of f. So if you go back and look at what we just observed about x cubed, when we took the derivative of it twice, we obtained 6x. And that means that 6x is the second derivative of x cubed, and then we can keep going. So the third derivative of x cubed would be 6. That's what we get if we apply the derivative operation 3 times. The fourth derivative will be 0. And if we keep going from here, taking the fifth derivative, the sixth derivative, and on, well, we'll just keep getting 0 because the derivative of 0 is 0. Now here, if eventually we got to a point where we just kept getting 0 every time, not every function is like that. Sometimes you'll have functions where if you keep taking the derivative again and again and again, you get a different function each time. But in this particular example, we ended up kind of bottoming out at 0. Let's look at an example in which we find a third derivative of a function. So our goal will be to find the third derivative of the square root function, the square root of x. Recall that we already know what the ordinary or first derivative of the square root of x is. It's 1 over 2 times the square root of x. For the sake of finding further derivatives, higher order derivatives, it will help to rewrite that as 1/2 times x to the power negative 1/2. We'll then be able to apply the power rule a couple of times. So let's find the second derivative of the square root of x. We're going to take the derivative of the square root of x, so the derivative of 1/2 times x to the power negative 1/2. And if you apply the power rule here and the constant multiple rule, you will get this, -1/4 times x to the power -3/2. That's the second derivative. To get the third derivative, we apply the differentiation operation once more. So we're now taking the derivative of -1/4 x to the power -3/2, and another application of the power rule and the constant multiple rules gives us 3/8 times x to the power -5/2. Or if you want to rewrite that in the radical notation that we started with, it would be 3/8 times the square root of x to the power 5. And there's our third derivative. So now we know how to find third derivatives or higher order derivatives in general. It just involves applying the same derivative rules that we've been using up to this point. Let's look at how we can talk about these using our derivative notation. We'll start with prime notation. So this is, in effect, Newton's notation, that where we use the prime symbol to mark a derivative. You can talk about higher order derivatives by including additional prime symbols. So to go back to our initial example, let's say that f of x is x cubed. That's our starting function. F prime of x is 3x squared. That we call the first derivative, or sometimes just derivative. And then the second derivative, which we saw was 6x, can be denoted as what you see there, f with 2 primes attached to it. If we put 3 primes, we'll have a symbol for the third derivative of x, or of f rather, and that'll be 6, and on and on. And we can read those symbols with the extra primes as f double prime of x, f triple prime of x, and so on. The only thing we run into here is that sometimes we might be dealing with a very high order derivative. So additional prime symbols are fine if we're trying to talk about a second derivative or a third derivative. But what if we need, say, a 14th derivative? Well, that's what the symbol would look like. It's not very efficient, and it's very hard to look at that and to see immediately that there are 14 prime symbols there. So instead of writing all those primes, what we typically do in this case is to put a little superscript parenthetical numeral indicating the order of the derivative. So this is how we would express a 14th derivative of f in this way. It's a little bit easier to interpret than that long sequence of primes. In practice, however, you rarely see this. Most of the time, we will not use derivatives of orders greater than 2 or maybe on occasion 3. But it would be very rare that we have to do something with, say, a 14th derivative. That's Newton's notation. What about Leibniz's d dx notation? The way we handle higher order derivatives here is by putting numeral superscripts on the d dx symbol. So here's what this looks like. If we start with x cubed, its first derivative would be what you see there, d dx applied to x cubed. The second derivative would be denoted like this. Notice the superscript 2's attached to the d and the dx. A third derivative would replace those 2's with 3's, and on and on. Now, this can be a little confusing because it sort of looks like we're talking about squaring here, but we're not. We're talking about applying the differentiation operation multiple times. What those 2's indicate there, or 3's or whatever they are, is the number of times that the d dx operation, what we call differentiating with respect to x, is being applied. Now, this also is a little confusing because we often read what you see there as d squared over dx squared, even though we're not really squaring anything in this case. You'll also sometimes see function names appearing in the numerator of the d dx symbol, as we've already seen. So if our symbol for a function is simple enough, then often we put it up with the d in the numerator there rather than putting it after the entire fraction. So we can write stuff like dy dx rather than d dx applied to y or something like that. And in this case, we still put the superscripts in the same place to denote higher order derivatives. So the second derivative of y here would be what you see there, d squared y over dx squared. The the superscript 2 in the numerator is still after the d, not after the y. Let's finish up this study of higher order derivatives right now by looking at one physical interpretation of a second derivative. Second derivatives are particularly important. Along with first derivatives, they are the most important ones that we study in calculus. You rarely need to worry too much about derivatives beyond those. You don't do much with third or fourth order derivatives. You might occasionally see something on the AP exam involving a very high order derivative, but that's usually there to test your knowledge of derivative rules and their patterns, not to figure out if you understand how to find a 28th derivative of a function. Now we're going to take a pretty close look later at second derivatives when we look at applications of differentiation. For now, we're just going to look at one particularly important and significant interpretation of a second derivative in physics. To get started here, we need to go back and think about position. So a lot of calculus was developed in order to study moving objects. And that's one of the big things we do with differential calculus. And as you are probably familiar with, if you have some way of assigning numerical values to locations, so if you can mark them off on some kind of number line or coordinate plane, for example, then you can treat a moving object's position as a function of time. And when we have these kinds of functions, they're often named using the letter S to denote position. That's coming from a Latin word situs that means placed, and that begins with the letter S. So let's look at an example. Okay, here's the situation. We're standing at the top of a tall tower. It's 57 meters tall. And we start dropping things off of it. We can denote the height above the ground of an object as it's falling down from the tower using this function here. S of t is equal to negative 5t squared plus 57. Here, t is the time in seconds after we let go of the object. Now, if that function there, s of t, tells us the falling object's position at a given time, let's think about its first derivative, which we could denote as s prime of t or ds dt. A value of this will be the rate at a particular time at which the object's position is changing. And that's what we call the velocity of the moving object. In other words, velocity can be defined as the first derivative of position with respect to time. And so if you want to know the object's velocity function and you already have its position function, take the derivative of the position function. Find v of t or s prime of t. In this case, for our example, that will be negative 10t. And the units for that are meters per second, since we're measuring distance here or position in meters and time in seconds. By the way, velocity is closely related, but not quite the same as something called speed. The speed of an object is its velocity if we ignore its direction. And mathematically, we can treat that as the absolute value of velocity. Now let's think about the second derivative of an object's position. So there's our position function. S of t is equal to negative 5t squared plus 57. We found that the first derivative of this, s prime of t, is the velocity function, sometimes also written v of t, and that is negative 10t in this case. Now, if we ask about the derivative of the velocity function, well, that will be the rate of change of the velocity at a particular time. And that's what we call the object's acceleration. And this measures how much the object is speeding up or slowing down at a given time. So acceleration is the first derivative of velocity. But we already saw that velocity is the first derivative of position. So acceleration is the second derivative of position. Now in our example, where s of t is negative 5t squared plus 57, s prime of t was negative 10t, and so s double prime of t is negative 10, a constant. This is also v prime of t, or a of t, where a denotes acceleration. The units for this are meters per second squared, or meters per second per second.